Hello, and welcome to our video on the Introduction to Statistical Thermodynamics. This is the last topic we're going to cover in this course over a couple of chapters. And here we're just giving you a brief introduction. This is obviously a subject unto itself of the idea of statistical thermodynamics. So let's first talk about what this is and what sort of motivates the research into this area and how it's useful. So when we're thinking about physical chemistry, there are sort of two main fields that we're thinking about often is quantum mechanics, where we're looking at individual molecules. So this is where we do things like find what are the energy levels of, say, a hydrogen atom, and find about s, p, d, f orbitals and all those things that you've learned about, and also things related not just to the electrons but also rotations and vibrations and the energy levels associated with those kinds of motions as well. So we're usually finding energy levels, and we are often solving this equation, the Schrodinger equation. If this doesn't mean anything to you, that's okay. Just for those who have seen this before, this is just a reminder, right? This is sort of our fundamental equation of quantum mechanics. And on the other hand, we often are not interested only in individual molecules, but we often want to think about, say, especially in thermodynamics, about bulk systems, right? So thinking about, like a mole of molecules. And what are the properties and what's the behavior of this sort of thing. And this is what we've studied in this class. We've studied thermodynamics of phase changes, of reactions occurring, and just to be clear, we often call this bulk properties. And what would be really great is to be able to bridge these two concepts, right? These two general areas of research or interest that we have in physical chemistry and chemistry in general. And so the question is there any way that we can sort of link these, that if we say know the quantum behavior, if we understand the energy levels of a molecule, can we go to the bulk properties, right? Can we calculate things like Gibbs free energy or entropy or things like that? And our bridge that lets us get between these is statistical thermodynamics, where we take what we know about individual molecules and use the ideas of statistics to scale that up to bulk properties, thinking about like a mole of molecules. Now, what is this useful for? Well, for one thing, if we can we have ways developed via quantum mechanics, we have ways to solve for energy levels. We have things like computational chemistry that let us calculate properties of molecules, things like energy levels, orbitals, these sorts of things. And it would be wonderful to be able to take those computed values or things that we measure via spectroscopy or similar things where we can measure the energy levels and use the results of those to predict bulk properties. So that's one of the major advantages of something like statistical thermodynamics, is that we can take these individual computations or measurements to predict bulk behavior. One other thing that we can get from statistical mechanics is, say we know bulk behavior, we can also sort of infer what's happening with individual molecules. For example, one thing that I'm particularly interested in as a spectroscopist is that if we can, there's a link between the distribution of molecules and energy levels, and that's linked to the temperature of a system. And so this is something where we're looking at individual molecule properties, but there's a bulk property that we care about, which is temperature. And so if we can either measure or predict the distribution of those molecules in their energy levels, we can infer the temperature of a system. So this is very useful in things where you can't put a thermometer in it to just measure the temperature. Say you're doing an experiment in a vacuum system like I do, you can figure out what temperature you're reaching inside of that experiment. Or if you want to do measurements out in space, you can look at the distribution of energy levels of molecules in space and infer what the temperature is there. So that's just one specific example of where statistical thermodynamics can be very useful. And so that's sort of my pitch as to what makes this an interesting topic. We're not going to go into super in-depth in this, but we're going to at least give you a flavor of the basic concepts of statistical thermodynamics and how we can go from individual energy levels to bulk properties and some of the equations involved with that.